Before we dive into the solution, let's understand the problem. Imagine trying to find a specific username in a social media feed that's constantly loading, or a transaction in a blockchain that grows forever. How do you search when you don't even know the end of the list? A common first thought might be, why not just use binary search? It's incredibly fast for sorted data. However, binary search has a critical weakness in this scenario. It needs to know the array's boundaries, specifically the high index, to find the middle. Without an end, you can't start. This is precisely where exponential search comes to the rescue. It's a brilliant two-phase strategy. It doesn't try to search the whole infinite list. Instead, it cleverly finds a small, manageable boundary first, and then performs a pinpoint search within that boundary. Let's break down this strategy. The magic of exponential search lies in its two distinct steps. First, the bounding phase rapidly finds a small range where our target element could be. Then, the searching phase uses the classic binary search to find the element within that range. Now, let's focus on phase 1, the bounding phase. The goal here is to stop searching the entire infinite array and instead find a much smaller, manageable block. We do this by making exponentially larger jumps, checking farther and farther until we've gone past our target. Here's the specific logic. We start our probe at index 1. We check if the element at this position is smaller than our target. If it is, we double our index for the next check, from 1 to 2, then 2 to 4, 4 to 8, and so on. This doubling is the exponential part of the name. We continue this doubling process until we find an index I where the element is greater than or equal to our target. This overshoot is crucial. It tells us we've gone past our target, meaning it must be in the block we just jumped over. This is our stopping condition. Once we've found our upper bound at index I, we know our target, if it exists, must lie between the previous jump point, which was I divided by 2, and the current point, I. This defines our final bounded search space. We've successfully turned an infinite problem into a finite one. With our well-defined range, we now move to phase 2. We have a small, sorted subarray. What's the most efficient way to search a sorted array with known boundaries? Binary search, of course. We apply this powerful algorithm only to the narrow range we just identified. Let's solidify all this with a concrete example. Here is our sorted array, and we're looking for the number 56. Let's trace how exponential search finds it, starting with phase 1. Phase 1 begins. We start our index I at 1. We check array 1, which is 5. Since 5 is less than our target of 56, the condition is met and we double our index. I now becomes 2. Our index I is now 2. We check array 2, which is 8. Again, 8 is less than 56, so we continue the process and double our index again. I becomes 4. Next, with I at 4, we check array at 4, which is 16. Still less than 56, so we double one more time. I now jumps to 8. Finally, our index I is 8. We check array 8, which is 72. 72 is greater than 56. Our condition, array I less than target, is now false. We stop. Our bounding phase is complete, and we have found our upper limit. Now we define our search space. The last successful jump was from index 4, which is our stop index, I equals 8, divided by 2. This means our target, 56, must be between index 4 and index 8. We'll now perform binary search on this specific subarray. Phase 2 begins. We apply binary search on the subarray from index 4 to 8. First, we find the middle index, which is 4 plus 8 divided by 2, giving us index 6. The value at array of 6 is 38. Since 38 is less than our target of 56, we know our target must be in the right half of this subarray. We discard the left half and update our low pointer to be mid plus 1, which is index 7. Our new search range is now from index 7 to 8. In our new, smaller range, we calculate the middle again. 7 plus 8 divided by 2 is 7.5, which we truncate to 7. We check array at 7, and its value is 56. This matches our target. We have successfully found the element at its original index, 7. So how fast is this two-phase process? The time complexity of exponential search is O log k, where k is the actual position of the target element. This is incredibly efficient, especially when k is small compared to the total size of the array. Let's quickly break down where O log k comes from. The bounding phase involves doubling our index I until it surpasses k. This takes about log k steps. The second phase, binary search, runs on a range of size k over 2, which also takes O log time. Added together, the complexity remains O log k. What about memory usage? Exponential search is very memory efficient. It operates in place, meaning it doesn't require any significant extra memory that scales with the input size. Its space complexity is O of 1, or constant time, which is a major advantage for massive data sets. This analysis leads to its ideal use cases. Exponential search outperforms a standard binary search when the target element is likely to be near the beginning of a very large array. And, as we saw, it's one of the best methods for unbounded arrays where the total size is unknown. However, there is one critical requirement that cannot be ignored. Like its second phase, binary search, the entire exponential search algorithm absolutely requires the array to be sorted. The logic of overshooting the target and then searching a range completely falls apart without this ordered structure. Let's place exponential search in context by comparing it to other common search algorithms. While linear search is simple, it's slow. Binary search is fast but needs known bounds. Exponential search combines the best of both worlds for its niche. It handles unknown bounds and is logarithmically fast relative to the target's position. So let's recap the entire process. Exponential search is an elegant two-phase algorithm. It first uses exponential jumps to rapidly find a boundary, then deploys a precise binary search to locate the target within that range. It's the perfect tool for searching the vast and the unknown, efficiently and effectively.